The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and thank you for joining. My name is Amy Rose. This is the fourth webinar in our India Modeling Spotlight series. And today we're talking about the Renewable Energy Potential, or REV tool. REV is a novel tool that NREL has been using for our own analysis in India and South Asia for many years to conduct wind and solar resource assessments, estimate the technical potential for wind and solar, and modeling the cost of developing these resources in specific locations through supply curves. And now with the recent open sourcing of REV, you can perform this analysis as well. So in this webinar, you'll learn about the model applications and a demonstration on how to use it. Our speaker today is Nick Grew. Nick is a geospatial data scientist at NREL. He specializes in renewable energy resource assessment and characterization using high spatial and temporal resolution time series data. Before I hand things over to Nick, just a few logistics. First, the webinar is being recorded and we'll make the recording available to you afterwards. Second, we will have time at the end for questions. So if you have any questions, please submit them using the questions pane on your screen at any time during the webinar, and we'll answer as many questions as possible at the end. So now, without further delay, I will hand things over to Nick Grew. Nick.
Hi, thank you, Amy. My name is Nick Grew. I'm a geospatial data scientist at the National Renewable Energy Lab, and I'll be discussing the Renewable Energy Potential Model, or REV model as we call it, and some work that we've done in India. So we'll start out with some typical questions that we're asking when we're setting about studying new places. So first one is, what is the PV generation potential for certain areas of India? Another question would be, what the potential electricity production for wind sites for specific places? And so before we had a broad geographic extent that we were quantifying the electrical output, but now we just want to focus in on some discrete locations. Another example is, how far away from existing transmission are sites with high resource potential? So you might have places with high capacity factors and low LCOE, but they might be really far away from transmission lines. And then what is the expected annual generation potential over the life of a PV plant? So if you've got a PV plant in the ground for 20 to 30 years, what kind of electrical output can you expect each year? A few others, what are the land use requirements and impacts of increasing levels of renewable energy potential deployment? What are the transmission and integration costs, and what's the resource variability? These are all important questions when we're trying to do energy modeling that are looking at, potential deployment 10, 20, 30 years into the future. So in order to help answer some of these questions, we developed the Renewable Energy Potential Model, or REV model, as I'll call it from now on. This is essentially a bunch of geographic and temporal analysis frameworks all strung together. We had been running this type of analysis, which we call technical potential and supply curve analysis, for many years, but it was a very manual labor intensive process. Every project would kind of start over with data, and we'd have to go through all the same steps again. And so developing this model was a way to really streamline things so that we could quickly iterate through different scenarios for different locations and different timelines, and really speed things up so that we can get results a lot faster. So what is the Renewable Energy Potential Model? So it helps us to assess the system performance, available capacity, distance to transmission, and the total cost. And so we can break these different areas into three discrete subsections. And so looking at the system performance and costs first, we might be looking for things like, what does solar and wind resource look like across time and space? And how do different systems respond in terms of electricity output? And so we're talking about different PV configurations, different wind systems. How might, little changes to the rotor diameter or the tilt, what would that do to the available capacity, electrical output, and supply curves. So on the available capacity side, how much land is available for deployment of solar and wind systems? We might see that there's a lot of open land if we were looking from a very high level, but once you start drilling down into culturally sensitive areas, urban areas, agriculture areas, all very important things, but may not jump out to you if you don't have the appropriate data. And then distance to transmission. So how far from existing transmission are potential solar and wind deployment sites? So this is a flow chart of the REV model. This is a pretty high level view of the model itself. And so starting in the upper left corner, we have a resource data set that I'll talk about in the coming slides. And so these are spatial temporal data sets that allow us to get an idea of the weather patterns and figure out the solar radiance and wind speeds that would impact solar and wind generation. We feed that data into the generation phase, which we actually use the System Advisor model, the SAM tool, which is also developed here at NREL. And basically we configure different wind and solar systems and run them against this resource data set to figure out what kind of capacity or what kind of electrical output can we expect with these different types of systems across different years. Then we calculate the site-based levelized cost of energy. And we do this through a few different ways, but the way I'll discuss is using the fixed charge rate approach. And so now we have a landscape of capacity factors and LCOEs, but the technical exclusion phase allows us to reduce the total available area by considering things like protected areas, urbanized areas, slope, any kind of water bodies or wetlands that we might be concerned about, we can remove from our analysis. And the supply curve model basically takes these remaining areas and connects them to the grid, and we figure out how far away are the existing transmission. Are there any kind of multipliers or capital cost considerations that would make places more or less expensive based on local labor rate, any kind of taxes, that kind of thing. And we rank these different discrete locations across a geographic plane and figure out where's the cheapest to most expensive locations, like where are the places that you'll get the most bang for your buck. And the representative profiles and aggregated profiles are basically things we do to make the data more digestible. And so we're producing lots and lots of data. Sometimes it can be multiple terabytes of data, and the representative profiles and aggregated profiles basically allow us to reduce that amount of data to something that's a little bit easier to analyze. The REV model is flexible in scope and scale. And so when we say this, we mean that we can run at a different geographic extent. So we can run for a single location. This would be very similar to the System Advisor model, the SAM tool that I was discussing earlier. You can choose a single location and run, a specific PV configuration or a specific wind turbine. We can also run a smaller subset than something that's subnational. We can run national scale, or presumably we can run the whole globe. So right now that's a little bit out of reach just because the solar and wind resource isn't quite there yet, and I'll talk about that a little bit later. But as more spatiotemporal weather data becomes available, that would become something that we could potentially do with this model. It's modular, and what I mean by that is, I mentioned earlier, it's a bunch of different analyses all strung together, which makes it really convenient because all the inputs and outputs are standardized. But for example, the initial stages of the model are the generation phase, where we're just calculating the capacity factors. And for a lot of projects, that's good enough. We don't have to continue down the whole flow chart of the model. And so you can basically, enter at that point and exit right at the beginning. Or you can, if you have your own custom generation outputs, you can insert that in the middle of the model and run through the end. It's all modular for that reason. So it's really flexible on what your specific analysis objectives are. The last one, temporal resolution. So we were using the spatial temporal data, but they come in different flavors. The NSRDB, for example, is half hourly for certain locations, and the Wind Toolkit, the Wind Resource Dataset can be 5 minutes. And the model can handle any of these different time resolutions, whatever you hand to it. It'll be able to figure out how to handle the data appropriately. So I've been talking about technical potential and supply curve analysis. It's useful to go over what the technical potential includes. So what can the tech potential analysis tell us? It basically establishes an upper boundary estimate of development potential. So looking at this pyramid here at the base level at the bottom, a resource potential looks at things like physical constraints, the energy content of the resource. So this is just getting an idea of across a geographic extent, what kind of what kind of resource quality are you seeing as you change location? Technical potential then starts to consider things like system and topographic constraints. So these would be, if you're running an axis tracker, you'll probably get more better capacity factors than if you were running a fixed tilt system. And then topographic constraints would be things like slope. So you can build in high slope, but it might be relatively expensive. And so we might exclude places that are over 5% slope or over 20% slope, depending on what kind of systems you're looking at. Land use constraints, these are things, like I said before, like national parks, culturally sensitive areas, and then the system performance where we're figuring out, given a particular solar or wind technology, what kind of electrical output could you expect? So that's kind of where that's where the REV model really excels, is in this technical potential realm. Above it, you'll see these other areas, the economic and market. And these are things that we kind of dip into the economic area. For example, the projected technology costs. We might look at, we might use sources like the annual technology baseline or other, local input for technology costs. So we'll figure out that, given in a certain year, the cost, the LCOE might be something versus 10 years out, it might be something different. So we'll dip into the economics a little bit, but things like market assumptions, where the policy implementation or regulatory limits, investor response, that's analysis that happens further downstream. So that's not really something that REV does. And I think that's important to note, because with the technical potential, we're not trying to figure out what feasibly could be developed. We're looking at what the available locations are and what kind of electrical output you could get for these places. Because a lot of people will see the technical potential results and it'll be a little bit of sticker shock because it's so much capacity. And that's on purpose, because we're trying to reduce the available area that other models downstream can further analyze and further investigate. So now we'll jump into some research questions. So we're wondering, we have some different research questions, and it's helpful to outline these as we're looking at different analysis outputs from the REV model. So first one is, what is the potential solar or wind or electrical output for various locations? So in order to do this analysis, we first need our resource data. And so for India, we have the National Solar Radiation Database, which covers other locations as well. But for India, we have data for years 2000 through 2014. And then we also have a typical meteorological year available as well. The temporal resolution is hourly for this data set, and spatial is roughly 10 kilometers. And it covers all of India and then parts of other, Southern Asia areas as well. I wanted to show this graphic. Hopefully it's not pixelated too much, but this is showing the time steps across a single day and how the NSRDB changes. So here it's kind of interesting because you can see where the clouds are that are reducing the DNI in this case, the direct normal irradiance. And so this is just a single day. And you can imagine when we have, for example, the 14 years that's available for India, how valuable this would be to get an idea of what kind of historical electrical output did you get, and you can get an idea of generally what kind of electrical output you might see in the future. So here, this little box in the lower left corner shows how the direct normal irradiance and the global horizontal and diffuse horizontal irradiance can change. So this would be for a single location, and you can see that you have a pretty good ramp earlier in the day where it must be pretty sunny, and then a steep drop off where there must be clouds crossing over. And so the direct normal irradiance and the global horizontal irradiance drop, but the diffuse changes goes up, and that must be because there's clouds that are bouncing and scattering the solar irradiance, so that would jump up. And so these are the kinds of things you can see in this data set. So now looking on the wind side, we use the wind toolkit. The temporal range is just for 2014, and the time resolution is 5 minutes, so higher than solar, but fewer number of years. The spatial resolution is also higher at 3 kilometer instead of the 10 kilometer. And this data set we have covers most of India and then other parts of Southern Asia. So you might be noticing that we have fewer years, and that's because it's harder to produce this data. There's been a lot of really great advancements on the solar side for developing lots of years of data using satellite imagery. For wind, it's more difficult. We have to use weather models to look at historical and future trends, and it's just more difficult. And so we're able to produce higher temporal resolution, like the 5-minute data here, but it's more difficult to get lots of years, and the data is really large as well. But as I'll talk about in future slides, that's something that we're hoping to rectify in the future. Same as solar, this is looking at this graphic here we put together to see, given a particular day, what kind of weather patterns would you see. And I think it's just fascinating looking at this because it almost looks like water flowing across, a geographic landscape. And so these are the kinds of things that you'd be able to see in the wind data. Okay, so now we have our resource data set, and we feed that into the system performance modeling phase of REV. And so here we're able to get the electrical output, and in the lower left, you'll see for different solar systems, how different decisions you make would impact the electrical output across a day. So the dual axis tracking, which is somewhat rare because there's so many moving parts, that gives you a lot of electrical output. But as I mentioned, some of the economic and factors that might play into that are that dual axis costs more. It takes more operations and maintenance costs to keep it running. Then you have things like no tracking flat, no tracking tilted east, no tracking tilted west. If there were a one-axis tracker in there, it would probably be in between the dual axis and the other fixed systems. And so these are different examples of how the decisions you make on the solar system will change your electrical output. Then on the right side, at the right bottom box, we have the wind power curves. And so these are 3 different turbines, for example. You can see that given the different assumptions you make with the wind turbines, you might get more electrical output or less for a given wind speed. And since the wind speed is so variable in a given location, that'll jump up and down throughout the day. Okay, so now we have an idea of the electrical output at different locations. So another example of a research question would be, what is the levelized cost of energy at these locations? So the LCOE is relatively straightforward unless you start trying to bring in a lot of complex factors to account for local labor rates, taxes, things that affect one location against another. If you're trying to get a good relative comparison from one location to another across a geographic extent, you can feed in the same capital costs and the same operations and maintenance costs and see how that's impacted by the changing or variability of the resource quality. So when we're calculating the LCOE, we use a fixed charge approach. And so the capital costs are an input, fixed operation and maintenance costs, the system size, and the fixed charge rate are used basically static if we don't have other local data that can help us figure out the changes in capital costs across a geographic plane. But then the net capacity factor changes based on the resource quality. And so that's what you're seeing on the right side here in this map. Basically, for this example, we haven't changed any of those other inputs. The only thing that's changing is the net capacity factor, and that's just from the resource quality. So you can see how that's a big jump. I mean, if you consider different labor rates or things, that'll change this map. But even just the resource quality, there's certain places that are between $14 and $26 per megawatt hour compared to, $44 per megawatt hour or higher. So just the resource quality can really change the LCOE. So now another research question: which locations are developable and how much capacity is installable? So this is getting into the technical exclusion and technical potential part of the model. And so here we layer a bunch of different GIS data sets on top of each other, including protected areas, urban areas, things like slope, culturally sensitive areas, and we try to remove these places from our input results. So looking at the map on the right side, you'll see these black areas and white areas. So the white areas are basically places that have been excluded, and the black areas are places that are still available. And so you have these circular areas here, and those are probably buffers. There might be a discrete location, like maybe it's a city or something, and we applied a buffer to that to exclude the general area around it from consideration. But then you have these really convoluted areas where there's all these small areas that are available, but they're kind of surrounded by this twisting and winding and warping other locations that are excluded or available. And this is most likely due to slope. That's a big driver of things like that. And so you have these really mountainous regions that can be, you have these small little areas that are relatively flat, but then right next to it are steep cliffs or something. And so it can make for really, as I said, convoluted maps like this, where it's hard to get a good idea of, well, what's really available and what isn't. And so this is what I mentioned earlier, the technical potential. This is where some people get kind of hung up on those results, because yeah, if you were to count all of the available area here, it would be a lot. There would probably be, hundreds of gigawatts or terawatts worth of capacity if you didn't further try to remove locations from consideration. And so that's what I mentioned earlier, where downstream analysis will try to figure out, well, of the available area left after the tech potential, what's realistically developable. So this is an example of that. So we applied all of our exclusion data sets to exclude places that we knew we didn't want to make available in our study for solar wind development. But then we did another step to further refine what we would consider, areas that are potentially developable. And even these are probably overstated. And that would be on purpose, because, the analysis is just trying to get a good idea of what's available and not exclude too much. So looking at these maps for wind and solar, most of the country was removed, but there's these certain locations here that we're investigating further and figuring out, well, how much capacity could you install? What kind of electrical output could you potentially get depending on the system configurations you're using, and so on. So you might be asking how we go about actually quantifying the capacity. So we use the power density approach, and this is based on some previous research done at NREL, where researchers essentially looked at different solar and wind systems and figured out just how much land they take up. And so to calculate the total capacity of a given area, we'll look at, for example, with the PV plant, we'll look where are the actual panels sited, but then, there's usually a fence or some other auxiliary land around these PV panels that are still considered part of the PV plant. And so we'll include that land as well. And that gives us, the total area, and then we can figure out for that PV plant what kind of capacity was installed there. And so we came up with roughly a range between 28 and 36 megawatts per square kilometer for fixed tilt. one axis tracker is a little bit different. One axis tracker is instead of being, a max range 36 megawatts per square kilometer, it's closer to 31 megawatts per square kilometer. And then on the wind side, same thing. It's a little bit more difficult than PV because there's so much land in between the wind turbines because you really have to space them out. So we came up with a 3 to 5 megawatts per square kilometer power density for wind. And so, you need a lot more land, but the land use is much less consumptive for wind. You can do things like, you can have agricultural lands sited alongside the wind where that might be more challenging with PV. And so taking this power density approach, we can take the available area and multiply that against the power density. And then for each location, we have the net capacity factors and then multiply that by the number of hours in the year. And that gives us, for a certain location, the total electrical output. And so just like capacity, if you're looking at a broad geographic extent, this number is going to be very big. But when you drill down into specific locations and really try to dive into specific factors for one location compared to another, you can start to get an idea of what kind of electrical output you can expect and how different weather patterns could affect the year-to-year generation of electricity. So last research question, what is the levelized cost of transmission, the LCOT, for these locations? So before we were talking about just the costs for developing the site. We were ignoring anything about connecting it to the grid. And so this research question and the later stages of the REV model help us to get a better idea of how transmission costs would affect the overall cost of the project. So here I'll use an example. We have our little sun icon here showing a example PV plant. And then all of these different colored lines here are transmission lines. And so this data came from OpenStreetMap. There's, of course, other data sets out there, but this one, for an illustrative purposes, this came from OpenStreetMap. So for each location, our little PV plant, we have lots of potential places that it can interconnect to. We have substations that are nearby, transmission lines that are all kind of around it. We have big load centers, big cities that might draw a lot of electricity. And we're trying to figure out what's the cheapest point of interconnection. It might be that it's just somewhere that's right next to it. It could be a little bit farther down. Perhaps there, it would make more sense to try to interconnect into a congested node. And so here we try to figure out what are all the potential connections for this particular site, and we rank these connections based on cost. And so if we were trying to cut into a transmission line, it would cost more because you would basically have to build a substation to tie that line into it. And so that's something that we consider. Whereas if you were to just tie into a substation, perhaps there's already bays that are available and the infrastructure is already there. And so it might be cheaper to just tie into a substation, but perhaps long-term, that doesn't make sense because it's less congested. These are just examples. And so for this example here, perhaps this line here was chosen to be the cheapest. Maybe this was the cheapest location. Maybe it had to build a substation, but when it's compared to all the other potential connections, maybe that was the cheapest. So when we're running this analysis, we're not just looking at a single location. We have lots of different places that are competing against each other. And so here in this example, we're seeing lots of PV plants all scattered across the geographic plane, and they all have to compete against each other. And as they connect to the transmission, the available capacity in the transmission lines is going to go down. And so you might have locations that try to connect to a relatively cheap area, but perhaps a PV plant earlier on in the modeling already connected there. And so, our focused PV plant might have to go to a little bit more expensive connection instead. And so here we see that for this example, all of these different PV plants try to interconnect to different features, and they're basically trying to optimize the cheapest location they can interconnect to that still has available capacity. So considering the transmission costs, in this plot, they're called the spur line cost, and the spur line is basically just the line from the PV plant to the existing transmission. You can really get an idea of how that transmission costs might impact things. And so in this example, the blue line is just the site LCOE, but that's totally naive of any interconnection costs. And so the gold line above it shows the impact of the interconnection cost. And so it really jumps. In certain places, you've got $75 per megawatt hour when we're looking at the cumulative capacity, and that can jump to, $105, $110 per megawatt hour, given whatever kind of transmission availability dynamics were happening in that particular location. And so basically looking at this plot, we're going from the left to the right, looking at the cheapest sites to the most expensive. And the cumulative capacity is basically ranking all of the available area depending on its resource quality, or in this case, the LCOE in dollars per megawatt hour. And so we basically have the cheapest locations on the left side and the most expensive on the right. And we start adding cumulatively all of this capacity to figure out where is the cutoff point. If you're looking for all capacity, for example, under $75 per megawatt hour, how much capacity can you get before you start breaking that threshold? So in this analysis, we're seeing that's happening at roughly 2,500 gigawatts, which is a lot. That's a ton of capacity, as I said, but this is getting back into that technical potential consideration I mentioned before, that not all of that 2,500 gigawatts is going to actually be available. Further analysis to look at the market and economic potential would be needed to figure out what's realistically developable versus something that probably wouldn't be developed. So tying this all in together, we can get our supply curve. We can figure out for different regions what's the typical site and transmission LCOE. And so this little bar plot at the bottom left side, we can see there's certain locations, for example, model region 7 has really high site LCOE, but it has relatively low transmission LCOE. So if there were certain ways to reduce the site LCOE, perhaps that would be a more economic area. So we're able to build out these different, we're able to figure out these different dynamics that could happen for a given geographic area based on the LCOT and LCOE results from this analysis. And then also, as I mentioned, the transmission availability, you might have a lot of really great resource that's really far away from transmission. And so we're able to use this analysis to figure out, well, the LCOE is really low for the site LCOE is really low for a given location, but the levelized cost of transmission is really high. And so perhaps if some investment were made for certain locations that reduce that distance gap, those really great resources might be more economical. So just kind of winding up here, the really beneficial part of the REV model is that we can make these iterative changes to our scenarios pretty fast and run things again and change things up and run it and compare the different scenarios to each other. Whereas before we had this model, it was really manual labor intensive, where we had to go back and find our data and change things up manually. But instead of doing that, we can basically, for example, here take one scenario where we have a solar system with a 20-degree tilt angle, but perhaps we decided, well, maybe 20 degrees isn't a good assumption, and so we changed that to 25. Rather than going back and having to put all our data together and manually change things and process our data and run this analysis, you're basically going into a config file, just a text file, changing one number and launching it, and it'll run through everything again and give you all the outputs in a standard result. So it really reduces the time, and it also reduces any kind of human error that might be injected. If somebody did one thing the first time and something different the second time, it reduces the possibility of doing that. And so it really makes for more robust results that you can get faster and compare the data results between different scenarios and know that you're getting the same kind of output, just with differing input assumptions. So the results from REV can be used for their own analysis, or they can be used for downstream models. So some examples of the results. So we're calculating the resource availability, figuring out areas that are available for development, looking at the performance of different solar and wind systems, and figuring out the cost of these systems. And those results can be used in things like production and capacity expansion models. We can do renewable energy zones analysis, figuring out if it makes sense to make certain places more economically viable given legislation or policy. And then also look at how different policy decisions might impact available land or potential electrical output. Looking at these different models on a graph here, we have our capacity expansion models in the green, the production cost models in the blue, and then the system advisor model down in the purple. And each of these models work in different geographic and temporal scopes. And so the REV model can work with each of these models, some of which are available open source. READS, for example, is another NREL tool that's also open source along with SAM. And so some of these tools are available to the public, and you can, since the REV model is open source, you can use these different tools together to produce different research products. So I listed these public resources here. They'll be made available in the slide deck itself when that comes out. But these are all things that you can look for. I mentioned the solar data and the wind data that we use. That's all available on Amazon Web Services, and so you don't need to download all this stuff and try to secure this on your local drive. You can pick out different locations and download them, and you can just pull them through AWS instead of trying to come up with your own data. A lot of all these models are available on GitHub. A lot of them are open source, and so you can actually go in and request for features. You can see how we do things, and if you have a different approach, you can change that to fit your own style. And so these are all valuable things to look for if you were interested in diving in further. So that's the end of the presentation. I wanted to go through real quick an example of running a model. There's different ways that you can run the model. And so we put together some slides on how the general public might approach running this model. So you can run REV either through Bash on the command line, or you can run it through an actual Python emulator or in Jupyter Notebook or something. So that's what we're seeing here. And so if we wanted to run a particular solar system here, this SAM config here matches what the system advisor or SAM tool would be expecting for a certain PV plant. And so here we see, our azimuth is 180 degrees, so that's south facing. The DC to AC ratio is 1.3. We have our losses set at 14%. This is for a 20 megawatt system, so that's in the system capacity, and so we're setting that there. And you can write out this input into a JSON config, and that's what the REV model would be looking for when it goes to run. For NSRDB, you can pull this data down from HSDS, or there's also ways that you can run the model from AWS itself. And if you go to the GitHub repo for REV, you'll see examples on that. But basically, we have this NSRDB sample file where we have a handful of points, and we load that into the model, and we create basically a set of points that we want to run. And so this might be 500 points. Each point is a different location. Sorry, I'll make that clear. So we might have 500 locations. We might have 1,000 locations. And so we're deciding, which points do we want to run and what kind of system do we want to run there. And so here's an example of the points. So we have, points at 15.05 latitude, 67.05 longitude. We can set which kind of system we're running there. Maybe some locations we want to run a one-axis tracker, while other locations we want to run a fixed tilt system. So this is where we would make those configurations. So now we have all of our points and the type of system we want to run, and the particular NSRDB years that we want to have available. Perhaps we chose year 2000 in this example, and we're running it through the model. And see, this code is basically kicking it off, and at the bottom you can see we're using PVWatts version 5. And so that's one of the models that's available in the SAM tool, but there's other versions of PVWatts. So version 7, for example, takes into account different things that perhaps version 5 didn't. And so here you could set what kind of solar modeling you want to use in the SAM tool, or if you're running wind, you would change the PVWatts v5 to the wind power module. And so this is where you have control over what kind of model you want to use and what results you're getting. So here we're asking for the capacity factor, the mean capacity factor across the entire year, but also the capacity factor profile. So given the input time steps, it could be either 5-minute, half-hourly, or hourly, give us the actual electrical output for every time step. So the results of this ends up being so for this, we're looking at the capacity factor profile. So we see that's an 8760 by 100 shape for the CF profile data set output. And so that's 100 different locations, and we get the actual hourly across the year potential capacity factor output. But then the mean capacity factor just crunches all those 8760 numbers together and gives us, for every 100 locations, what's the annual capacity factor potential. And so there's lots of different potential outputs you can ask for. You can ask for the plane of array irradiance. Perhaps you want the pressure or the wind speed at these locations. Those are all things that you can ask for to supplement your analysis. So that was a quick overview of how you can run the model. There's lots more examples available at the GitHub repo. Once these slides come out, feel free to poke around and try it yourself and see what kind of outputs you can get. And with that, I'll hand it back over, and thanks for listening, and happy to answer any questions.
Great, thank you, Nick. We do have quite a few questions, so we'll try to answer as many as we can. First, there are several questions about data, input data and assumptions and data sources. So related to wind and solar resource data, there was a question, have we considered using other data sets, particularly for wind, where in India we only have 1 year of available data? So we considered looking at Global Wind Atlas or other data sets.
Yeah, and that's a great question. Yes, yep, Global Wind Atlas is a great resource, and we have used that before. There's other reanalysis data sets out there as well, like MERA 2 and ERA 5. Those are kind of spatially coarse, but the Global Wind Atlas is great, and that's where I mentioned you can kind of inject different data sets into the model and use them instead of the default inputs. And so there, with the Global Wind Atlas, for example, unless you paid to get the actual time series data, maybe you only have that multi-year mean capacity factor. And so you can structure that data into a way that the REV model is expecting, where you don't need the actual profiles themselves. You have these multi-year mean capacity factors, and you can input that into the model and go ahead and keep running and do your technical potential and supply curve analysis. And so yes, the REV model is flexible enough to use that, and we have certainly used that in places where we didn't have available time series.
And then on our transmission data, we have two questions. I'll try to combine them because they're related. So what have we done to verify that the data is correct, and how confident are we in our transmission data? And what do we do about updating the data as new transmission reinforcements and substations are built?
Yep, that's a great question. And I did mention we use OpenStreetMap for that particular analysis. Yeah, that's something that we kind of have to deal with all the time. Using OpenStreetMap, it's kind of open. It's open to whoever wants to input data, and so we don't have a lot of visibility into how accurate that data is. And so basically, we have to make that assumption and make sure that the client is okay with it, depending on what kind of analysis we're doing, and just make sure that we are aware of the shortfalls of using open source data. a lot of times, if at all possible, we'll try to get our client to give us the actual official data, but there can be some security issues around that, and sometimes, you know, whichever local stakeholder we're working with doesn't want to share that data with us, and so it really is just a case by case issue that we have to deal with every study. We try to get the most accurate data we can, but it's sometimes we have to fall back on data that's available, but we have a little bit less visibility into how it was used. In terms of updating that data, I guess it depends on who's going to be using it and what the purpose is. You know, if the data is not sensitive, it can be uploaded to OpenStreetMap, and then more researchers can use that data for their own analysis. Otherwise, you know, if we have a particular study and we're working with a local stakeholder group, we would just ask for, if we're running that through our model, we would essentially ask for that data from the stakeholder and try to get that in some kind of GIS format that we can use in the model.
Okay. Kind of a related question. Someone asked, what could people in India do to improve data collection? Are there any specific areas where you think we can improve our India assessments?
Yeah. So what has been really helpful in the past is when there's an actual state-run geospatial clearinghouse or portal where all these data sets can be housed together. That's been really helpful because it's a one-stop shop where we can go and pull GIS data sets or other data sets that can help in our modeling. And if it's made available to the public, that's even better, because people might have insight into their local area that they live or they work. And if they can upload that data into this shared website or web portal and make it available in some kind of tracked environment where the author is tracked and the source of the data and some kind of validation effort is done on the data, that can be really make it a lot easier for us to collect data. Because if we don't have a place to go for downloading this data, we basically have to do Google searches and try to find what's available. And so I know for India, land categorization is difficult to find recent data. We have globe covered data from 2009, but that's over 10 years old now. And so any kind of advancements on land categorization, either using satellite or ground-based analysis, if that can be made available in some kind of official web portal where we can go and download the data, that just makes the analysis better.
Definitely. Then just a couple more data questions, and then we can go on to others. Could you comment on how REV accounts for O&M costs for a specific make of wind turbine over its whole lifetime?
Yeah.
This is variable and fixed.
Right. Yep. So we when we're using the maintenance costs, if we have, so depending on where we're working, we might have a general maintenance cost input that we'll use. And so, in certain places that we're working, we have a single number, maybe it's, $14, per megawatt year, or something like that. And somebody has already done the work to kind of produce these annual estimates of operation and maintenance costs. But sometimes if we have one particular system that the client wants to use, perhaps it's a single, specific wind turbine, we would basically go and ask the client to provide some kind of estimate on the operation and maintenance costs for that. When we're running wind and solar systems, we don't use the variable costs. We kind of tie that into the capital costs and the fixed operation and the maintenance costs. But that's something that we would try to get from either the manufacturer of the systems or from the client if they have some kind of idea of cost. from, you know, building that system previously. Maybe they have different types of systems that they can give us an idea of what kind of O&M costs they've experienced over the years. We would try to use that as an input.
Okay. And then the last data related question. Oh, I lost it. Okay. What was the difference between pulling solar data from the NSRDB and Amazon Web Service?
Oh, sorry. So they're the same data set. The NSRDB is the data set, but basically you have a few different options. The NSRDB is available for download through the NREL website, but you can also download it through AWS. But there's also ways that you can actually run the model itself in AWS, so you're not actually downloading the NSRDB data set. You're basically streaming the resource data across the internet without having to download it. And so that, you know, if you have any kind of storage constraints on your local computer and you can't download that data, you can basically fire up you know, an AWS node, or you can run it on your own computer, but stream that NSRDB data set without having to download it itself. And so an example of streaming that data from AWS is up on the GitHub repo for Rev.
Okay. Well, I'm glad you pointed that out, because there was a question about, is there a user guide for the Rev model to help those people who are interested start understanding the model and how to run it?
Yep, and here I'll put up these links here again. So yeah, if you were to go to the Rev landing page, this top one here, the Rev GitHub repo, all of those have different resources on running the model. There's different resources here, including the Rex. That's basically a helper tool that can help you to download NSRDB or WIN data, convert it into some kind of standard structure for running in Rev. Then the System Advisor model, that's also open source on GitHub, but I put the sam.nrel.gov site here. So all of these resources here, especially the Rev landing page and the Rev GitHub repo, are good starting places to figure out how to actually run this. There's documentation up there. There's documentation on the functions, the actual Python code, but also feel free to email us. At some point, you're going to be reading through the documentation and you might hit a gap or hit a wall, and you should definitely feel free to email us here at NREL. And all of our contact information is up there on those landing pages as well in the repos. And so feel free to reach out and we'd be happy to help fill in any gaps in the documentation.
Great. And then some questions kind of on the model itself and what it does. Oh, this one came in almost right away. I love this question about, are we able to model wind and solar hybrids in Rev?
Yeah, that's a question we've been getting a lot recently. At this point, that is, at this point in the Rev model, we would basically run a solar system and a wind system at the same location, and it might be naive to whether the land was being consumed by the PV panels or not, whether you could actually physically sink a wind turbine in a place that already has solar panels. And so, no, I would say that that analysis right out of the box is not what you'd be expecting, but there's ways that you can handle that, looking at changing the land availability. So if you want to focus on areas that maybe have the high capacity factors for solar, you might then on the wind side make that land unavailable for wind development. And so then you wouldn't have this overlapping solar and wind on the same location. So it would take some processing up front to do that at this point, but we've definitely gotten a lot of interest to do that kind of analysis. And so there's already been some initiatives moving forward trying to figure out how we can model that. So I'd say that's something that's in development to integrate it better into the Rev model, but there are some ways to try to do some initial analysis, but it would just take some more manual processing at this point.
Okay, so something to look forward to.
Yep.
And then a couple other questions on the model. So how do you calculate LCOE for a region instead of a single spot?
Yeah, so in order to calculate for a region instead of a single spot, the approach that we take is to calculate the LCOE for every single spot in that region, and then do some kind of average or find the median or find the maximum or minimum. We maintain that high spatial resolution so that we can really dig into a site-specific relative analysis from one site to another. But when we're trying to figure out for a given region, we'll average those up or find the median.
And then this is related to kind of linking models together. So does Rev look at hourly data to determine the curtailment?
Yeah, that's a good question. At this point, we are not running as much curtailment because, we're not really considering curtailment because we aren't necessarily considering load or the actual demand for the electricity. And so that's not something that we specifically focus on most of the time. But I will give an example where we were curtailing for things like wildlife considerations. And so that was a certain study we did looking at endangered bat species, where we knew that these species were active in, kind of the twilight, dawn, and dusk timeframes. And so we chose to reduce the electrical output of wind turbines in this example during those periods. And so we were effectively curtailing the wind turbines from working during dusk and dawn when these bats were highly active in these certain locations. And so, yeah, it takes a little bit of manual processing because we're physically telling it between certain hours, if the wind speed isn't above a certain threshold, don't allow the turbine to start up. But in terms of curtailing because of, a saturation of electricity in a given transmission infrastructure, that's something you could do. But again, it would just take some manual processing at this point. If that's something that you want us to consider, certainly go to the Rev GitHub repo and put up an issue, and that's something that we're definitely happy to contemplate and try to figure out how we could run it in the model.
Great. Actually, a kind of related question. Someone had asked who we typically work with as clients, whether it's power companies or national grid companies.
Mm-hmm. Yeah, it's kind of all of the above. We definitely work with utilities. We work with country and state governments, different power companies. Yeah, I mean, transmission operators, lots of different clients. So yeah, I wouldn't say we're restricted to any individual group. It really is anybody that's interested that would like us to help in their analysis. We can start the dialogue going and figure out how we can support them.
Okay. And then I recognize we just have 1 minute left. So just in closing, we've had a couple of questions, kind of specific questions about the installation process. Some people get hung up on like PySAM or specific steps there. So what would you recommend for people to get support if they're trying to install Rev and run it themselves and they're getting stuck?
Mm-hmm. Yeah, well, in the later stages of the slides here, I didn't show there's some steps to install that. So, once you get your hands on these slides, feel free to scroll towards the end and you'll see some help there. Otherwise, yeah, I would point you to the Rev GitHub repo to look for examples, and feel free to reach out to us and send up a GitHub issue in the Rev GitHub repo if you're having trouble. Our software developers and the analysts will see that and we'll be able to figure out if perhaps there's something we didn't consider, if there's any gaps in our installation approach that we could help make this more streamlined.
Okay, great. Well, I want to say a big thank you to Nick for his presentation on Rev, and thank you all for joining us today. If you have any questions about this or any of our previous India Modeling Spotlight webinars, Please feel free to reach out. You can email me, Amy Rose. If you have questions on Rev, as Nick mentioned, you can reach out to him. And I'll be sending out a message, an email today or tomorrow with the slides and with a video recording of this webinar in case you want to look over it again. So thank you all very much and have a great day.
Thanks, everybody.